Okay, we're ready for section 6.1, graphs of the sine and cosine functions. A couple of things that we want to recall. First of all, if a function is odd. Then if we were to plug in the opposite sign of our input value, it should equal the opposite y value. A perfect example of an odd function is x cubed, because if we were to plug in the opposite of x and we were to cube that, we would still get the opposite of x cubed. So it's the opposite of the original function. And notice if we were to graph that odd, it looks something like this. If a function is even and we plug in an opposite input value, we would get the same y value as f of x. A perfect example of that, again, is x squared. If we were to plug in the opposite of that input value and we were to square that negative, we get the original function back, x squared. And again, an even function is symmetrical here about the y-axis. So some of our functions that we're going to be working with in trigonometry will be odd and some will be even. Also, we still have these same transformations that we've had all along. It's just some of those transformations may have a different name. For example, if you have an a outside the function, that's still our vertical stretch. Oh, that is written wrong. Looky there. It's a vertical stretch if a is greater than 1. And a compression if a is between 0 and 1. If a is negative, it means it reflects over the x-axis. For b, the number that's being multiplied by our x here or here, it's a horizontal stretch if the b is between 0 and 1, and it's a compression if b is greater than 1, and then it reflects over the y-axis if b is negative. Now, one of the things I want to recommend for you guys, factor out the b no matter what. I know that sounds weird. You don't normally only factor it out if it was a GCF, but that way we can tell for sure b is the horizontal stretch, and then this value that's left here, the c over b, would be your horizontal shift left or right. And d is still your vertical shift up and down. That is true for any function. None of these have changed. They'll just have some different names with the trig. So here's a new definition. A periodic function is a function that repeats its values in a consistent pattern. So the length of one full cycle of the pattern before it starts to repeat is called the period. For example, the circumference of the unit circle is 2 pi, because our r is 1. So the least value for which the sine and cosine functions start to repeat itself would be 2 pi. Thus, the period of the sine and cosine function is 2 pi. So sine of x is the same as the sine of x plus 2 pi. Cosine of x equals the cosine of x plus 2 pi. So let's graph sine of x. Instead of working with a unit circle, we're going to work with x and y coordinates as if the x value is your input or angle, and y is the output value of your trig function. And as we go from 0 to pi over 2, and again, we're looking at just the sine right now, then our y values goes from 0 and pi over 2, it goes up to, I'm going to label this guy 1 and -1. So we'll be going by halves. So it will come up here to 1. For the sine function, in the second quadrant from pi over 2 to pi, it moves from 1 down to 0. Then at 3 pi over 2, it goes down to -1. And at 2 pi, it goes back up to 0. Your trig functions are nice, smooth curves, so you don't want to connect these with sharp lines. It's going to look something like this. So this will always be the shape, the parent function, that may have some stretch, compressions, or shifts. Now this is just one period. We've gone from 0 all the way over to 2 pi. Notice the shape does not repeat itself. But if we know that it's periodic, then that shape continues on the left-hand side. And it will go like this forever and ever. So this is a picture or a graph of a sine function over 2 periods. with no transformations. So the domain, notice it covers all values of x. So we're going from negative infinity to infinity, keeps going on and on forevermore. But the range is only from -1 to 1, and they're included, so we use the brackets. The period is 2 pi, which means that's the length of the graph before it starts to repeat itself. So if we look at just this guy here, if we were to keep graphing it, it would repeat itself and keep going. We also want to look at the symmetry. Notice there in the middle, it kind of looks like, if we were to zoom in, it kind of looks like a cubic there in the middle. This is what we call being symmetric with respect to the origin. So the function is odd. In other words, if we were to plug in the opposite x value, we would get the opposite y value. So notice up here at pi over 2, we're at a +1. But at negative pi over 2, we're at a -1. At positive 3 pi over 2, we're at -1. But at negative 3 pi over 2, we're at a +1. So opposite x values gives us opposite y values. It's odd. Now for the cosine function, let's label this 1 and -1. At 0, our cosine value is 1. It's 0 at pi over 2, -1 at pi, 0 at 3 pi over 2, and 1 at 2 pi. So it looks like that. So this is just one period of the function. But if we were to continue this graph over 2 periods, it would look like this. So again, one full picture before it starts to repeat is 2 pi in length. So our domain is again from negative infinity to infinity with a range from bracket -1 to 1, close bracket. Our period is 2 pi, but this time our graph is symmetric with respect to the y-axis. So that means we have an even function. If we were to plug in an opposite x value, we would still get the same y value. For example, here we plugged in pi over 2 and we got a 0 for our y. But if we go to negative pi over 2, we still get 0 for our y. At pi, we got a -1 for y. At negative pi, we still get a -1 for our y. So opposite x values give us the exact same y values. You may also notice that this does look similar to our sine graph. It just looks like it's been shifted over. Well, you're right. The graph of the cosine x value is the same as the sine function shifted or translated pi over 2 units to the left. So now we want to take a look at trigonometric functions with transformations. So this is the generic form of what they call a sinusoidal function, a sine function or cosine function with transformations. Notice on this line here, the b values have been factored out. So we still have a vertical stretch or compression by a factor of the absolute value of a, just like before. But with trig functions, we call that the amplitude. The amplitude of a periodic function is half of the difference between its maximum and minimum. Think of the distance. So it describes the height of the graph both above and below what we call midline, which passes through the middle of the graph. So here's an example of a sine function that has not been shifted left or right or up or down. So the x-axis is still our midline, and the amplitude is the distance above that midline. The horizontal stretch or compression factor is the absolute value of b, and this value affects the period, where we take the standard period, which is 2 pi, and we divide it by the absolute value of our b. The horizontal shift is found after b is factored out. This is called the phase shift. And if factoring out that word kind of freaks you out, that just means you're going to take whatever that c value is and divide it by b. And remember, those horizontal shifts left and right still work in the opposite direction of the sine of c over b. We also have the vertical shift No new name there, it's still a vertical shift, and that's our D. And that vertical shift still moves in the same direction as the sine of D. The midline is given as the equation y equals D. In other words, your midline is always your x-axis until it gets shifted up and down, and then that midline shifts as well. Just like our asymptotes would move left and right, that midline moves up and down. In this box here is guidelines for sketching the graph. So I've kind of written out the steps of what to do, but instead of us walking through that, let's actually jump to an example first. So we're going to use the guidelines above to draw the graph of the function over just one period. And then we're going to check our answer with a graphing device, find the domain and range of the function. We first want to see if we need to factor out our b, but notice there's no other plus c or plus d there involved. So all we are working with is an a value of -3 and a b value of 2. So remember, the absolute value of a, which is 3, is called our amplitude. The fact that it's a -3 means that it is reflected over the x-axis. And remember, we have the formula for our period is 2 pi divided by b, which in this case is 2 pi divided by 2. So we have a period of pi. We do not have any left, right, or up or down shifts, no horizontal or vertical shifts, just an amplitude, a reflection, and a compression or change in our period. We always want to start with the period. We're going to start at 0. And remember, we're dealing with sine, and that sine function always looks like kind of the S value. That's how I remember. The sine looks like an S, kind of inverted S. The cosine looks like a inverted C. So our sine function, we start at 0 and then mark your period out here at pi. Both of those are going to be at your midline. Remember your 5 points, you got 3 zeros, your first, your last, and your middle. And then in between those, you have your highest point and your lowest point. So let's label our axes. You have to label those axes. So I know I'm going to have an important number in the middle. So half of pi is pi over 2. And then I want to cut that guy in half. Pi over 2 times 1/2 is pi over 4. And then count. This is 1 pi over 4, 2 pi over 4. So this guy here would be 3 pi over 4. So now we've dealt with the period and the x-axis. Since our amplitude is 3, that means it's going to stretch. Instead of going all the way down to -1 and 1, we're going to go down to -3 and 3. That's where our amplitude comes in. So we can mark 3 and -3 here. So remember, your first, last, and middle are in the zeros. And originally, it would go up to your amplitude at pi over 4 and down all the way to your bottom amplitude at 3 pi over 4. And you would connect that to be your sine function. But we have one last piece, the fact that it's reflected over the x-axis. At the zeros, those guys stay because they're on the x-axis, but those other 2 points are going to flip. So at pi over 4, we're down at -3. And at 3 pi over 4, we're up here at 3. So that's our final answer. Again, before the reflection, it would have looked like that, where our period is pi, our amplitude is 3, and we have to split up that period. So we go to the midpoint and then the middle point of that, and everybody has one of those 5 main points. So point 1, point 2, point 3, point 4, and point 5. Those are going to be the points that I'm looking at to determine whether or not your graph is correct. I also need your x value to be labeled so we know exactly which angles you're looking at, which x values. And I also need your y's to be labeled so I know that you are taking it to the highest and lowest, whatever your amplitude is. So it's those 5 points I'm going to be looking at. Be sure that they're labeled. It doesn't have to be labeled on the point itself as long as your axis is labeled. In this example, we're still dealing with the sine function. So we know it looks something like this. again, over one period, and we want to find the domain and the range of the function. Notice here we have a b and a c value. So let's go ahead and factor out that pi over 2. Y equals sine of pi over 2 times x plus 2. Now, if you're wondering how we got that 2, let's do a little scratch work up here at the top. It would be our c value divided by the b value. So pi divided by pi over 2, which is pi divided by pi over 2, which is pi times 2 over pi. They reduce, and we just get 2. So this gives us a b value of pi over 2 and a c over b value, which is our phase shift, that's left to right, of a positive 2. Remember, we move in the opposite direction there. So to find our period, sine normally has a period of 2 pi, but we divide it by our b, which is pi over 2. When we reduce that, we actually get a period of 4. Pi is gone. Interesting. Okay, so we have a period of 4, and that phase shift tells us that we are moving left 2 units. So let's graph that. Since we're moving left 2 units, I want to make the left side here a little bit bigger. And we may have to graph this again in segments. We're going to start at 0, 0 before any phase shift. Our period is 4, so I'm going to go all the way out here to 4. Remember, we cut that in half, we get 2, cut that in half, we get 1. So 1, 2, 3. If we were to graph this, remember there's no amplitude change, no A. So we're still going up to 1, down to -1. The outsides in the middle are at 0. First one is up to our amplitude. Third one's down to our amplitude. So this first graph only deals with our amplitude, if there was a change, which there wasn't, and our new period. So now we have to do our phase shift. So we have to move everything to the left 2 units. So -1, -2. Everything gets shifted 2 units left. And that's our final graph. Now, in both of these examples, they asked us to find the domain and the range. So on top, example 2, even though they only asked us to graph it over one period, the domain of that function is still from -infinity to infinity. The range, however, has changed because the amplitude changed. It's stretched, and the range is going from -3 to 3 with our endpoints included. In example 3, we still have a domain from -infinity to infinity that does not change. And our lowest and highest points for our range is -1 to 1 using brackets. Now we want to check our answers using a graphing device. So for example 2, where y equals -3 sine of 2x, when we graph it on the calculator, we want to be sure that our amplitude as well as our entire period shows up. If we go to y equals, let's type in our equation, -3, and be sure you're using the negative symbol down at the bottom, sine of 2x, and here's our x to the right of the alpha button, close the parentheses. But we want to check our window. Let's make the window happy. We can go from -10 to 10, but notice over here to the right, I kind of copied down what our x-axis looked like, how we labeled it to get to that one period. So I would go from an x-min from 0, and we want our x-max to be pi. Notice pi is here above the caret to the right. And then our scale, notice we were doing it in pi's over 4. So we want the scales to be the same. Second function pi divided by 4. And our y-mins doesn't have to be that big because remember we only went from -3 to 3. So maybe go minimum of -4 to 4 by a scale of 1. And when we graph, it shows just that one period that we were looking for. Now for example 3, we have y equals sine of the quantity pi over 2x plus pi. Let's put that into our y value, sine parentheses, pi divided by 2 times x plus pi, close parenthesis. And we also want to change our window again because notice down here when we graphed that, we no longer were using pi for our x values. Instead, our final graph went from -2 to 2. So we want our x min to be -2, our x max to be 2. We want our scale to be 1. In other words, our hash marks are of size 1. And our y min and max were -1 and 1 on the graph. So maybe let's go out one more and go from -2 to 2. And we do, in fact, get the same graph that we got. So this is just a way to check what the graph should look like. But notice, in order to graph it properly, we kind of need to know what all of our hash marks, how they're labeled, so we can check it. You don't want to rely on your calculator to graph it, because if your window's messed up, you're not going to be able to tell what the period actually is. So in example 4, we're now dealing with cosine. And remember, our cosine graph looks something more like this, kind of an inverted C. And they want us to graph it over 2 periods. I would always start with 1 period first. Start at the origin, and then you can extend it. So let's figure out what our values are. Be careful. This is a -3 plus cosine. It is not multiplied, so that is not our A. This is actually our D value of a -3, which means we're going to move down 3 units. Now, I also want to factor out that 1/2. So if we get y equals, I'm going to move that -3 to the right-hand side. So we would have cosine of 1/2 times x minus 2 pi. I'm going to put that plus a -3 or -3 here at the end. So there's no A value, so our amplitude is going to stay at 1. So we've got up to 1, down to -1. We have a B value of 1/2, so that's going to change our period of 2 pi divided by 1/2 gives us a period of 4 pi. And then our phase shift, which remember is that C over the B, when you factor it out, gave us a 2 pi. And since it is a -2 pi, that means we're going to move right 2 pi. So we have a lot of things going on here. We're going to move down 3. We have a new period. We have a phase shift, but no reflection or stretch or compression, or at least no stretch or compression vertically. So let's graph this. I want to make it somewhat small because we are going to be wanting to do 2 periods, right? So we have a period of 4 pi. So I'm going to put my 4 pi here and then cut my halfway at 2 pi, cut that in half to give me pi. So this guy is going to be 3 pi. And we're dealing with cosine, so our graph's a little bit different. It's the pi and 3 pi that are going to be at 0. Amplitude is 1, so we're going to go up to 1 and -1. So cosine starts up at the top of that amplitude, hits 0, goes down, hits 0, and back up again. So that's what 1 period looks like before we've shifted down 3 and right 2. So now we want to do those 2 movements. We know we're going to go right 2 pi. So we're going to need to move over 5 pi and 6 pi. And then everybody moves down 2. So we're going to go down -2 and down to -3. So down 3, 1, 2, 3, and right 2 pi, 1, 2. Down 3, right 2. Extend this. Apparently I can't move 3 units. Down 3, right 2 pi, 3, right 2, and down 3, right 2. And we get this graph. And again, this is only 1 period, but we can copy this. We know what the graph looks like, so I can do another period to the left. Just be sure that they're all pi apart. And be sure and label them. So we have a -pi and a -2 pi. I know that looks kind of messy, but notice though they're not lines. It's still curves, and I didn't curve them very well here. So the domain is still from -infinity to infinity. The sine and cosines will always be from -infinity to infinity unless it specifically tells you that you're only going from 0 to 2 pi, unless it changes the domain for you. Our range with that final graph, our lowest point is -4, and our highest point is -2. Now we can check this again on our graphing calculator. So to check it, again, we want to put in our equation. And it's nice to put in the original equation before you factored anything out, just to double check. So we have -3 plus cosine of 1/2 times x minus pi, close parentheses. And again, we want to fix our window. Notice our x values, if we're doing 2 periods, we're going from -2 pi, x max would be 6 pi. And our hash marks were in terms of 1 pi. So we're going to put in a pi there. Our y values went from -2 to -4. So maybe go down a couple, -6 to 0. And when we graph it, we get the same graph that we did before. So we can check it against our graph that we have on our worksheet. Okay, our very last example, connecting graphs with equations. So now we're going backwards. We're given a graph and we want to find the equation that works. For the given graph below, determine a possible equation and assume that b is greater than 0. Remember, because the sine and cosine values can be written as the same function, we have a choice. We can determine if this is a cosine function or we can write it as a sine function. For my money, because at 0, it's already here and it starts to repeat here, that first pattern that I see is already in kind of a cosine shape. So I would probably choose the cosine function. Okay, so I would start with cosine x, and then I would focus only on this first period from 0 to pi. So if we have a period of pi, and remember period is 2 pi divided by b, we need to figure out what that b is. If we were to solve that, multiply both sides by b, you guys can probably see what it is without doing all of this, but just in case, divide both sides by pi, and we get a b value of 2. So we can write that as cosine of 2x. So that was our start, was to determine which shape are we going to be working with. And then we can figure out our period. Because we chose cosine, there's no left or right shift. So we don't have to worry about a c over b or, the x plus or minus something. It doesn't shift left or right. Also, if you look, the highest point, since our 1 is up here, our highest point is a half. Our lowest point is a -1/2, which means it wasn't shifted up and down either. So there's no d value. So the only thing that's changed is our amplitude. Our amplitude has been cut in half. So our amplitude equals 1/2. So that gives us the equation 1/2 cosine of 2x. And again, you can put that in your calculator, the 1/2 cosine 2x. Ooh, it's an equation, right? I forgot my y equals 1/2 cosine of 2x. You can always put that in your calculator, use the same hash marks, go from 0 to pi, and see if you get the same graph back. Good work, guys. I wish you luck. You know where to find me if you need help. Talk to you soon. Bye.